Alright, here we go again. Project Euler number 2. So this is all about even Fibonacci numbers. So we're going to define the Fibonacci sequence here. Each new term is given by adding the previous two terms. So if we start with 1 and 2, the first 10 terms are going to be 1, 2, 3, 5, 8, 13, 21, 34, 55, 89. Pretty well known sequence this. I think Mr. Fibonacci lived around the 12th century, so this sequence has been with us for I guess 1,000 years. It was probably discovered earlier than that, to be honest, wasn't it? Alright, so by considering the terms in the Fibonacci sequence whose values do not exceed 4 million, finds the sum of the even valued terms. I mean, there's a bunch of ways you can do this. I think one way is you could probably spot that. I think it looks here like every third one is probably going to be even, so you could probably just take every third one. But that assumption might not be true in general. There's a famous issue of, if you've got a circle and you divide it into sections, and you with straight lines, you sort of get a number of divisions, and the way that goes is obviously 1, 2, 4, 8, 16, but then it goes to 31. So patterns don't always work, right? So I can't prove it instantly, so I'm not going to assume it. So we'll do this kind of brute force-ish way where it's first we'll generate the Fibonacci sequence, then we will select only terms that are even using basically the same remainder thing we did in the first problem, and finally we're only going to consider those terms that are less than 4 million. An interesting thing to think about with this sort of problem is are you allowed to use integers? The answer in this case is yes, and you can do a sort of back of the envelope calculation with this, if you compare the sequence to powers of 2, and take some logarithms, you will eventually see that if we sum stuff that's a geometric progression that's less bad than powers of 2, it's always going to be less than the maximum integer, which is 2 to the 31 minus 1. But that's kind of irrelevant for this whole thing, really. I'm just going to take it for granted that we can. So usually what I do in Scala when I want to generate a sequence that's based on the previous things in that sequence is I'm going to go ahead and use iterator.iterate. So the way this works, I mean, if you know how it works, you know how it works. If you don't, it works like this. So you have some starting value, then you've got a function that you apply to that starting value, and each next thing in your iterator is going to be applying this function to the previous value. So for Fibonacci numbers, we kind of need to keep track of two things. We need to keep track of the previous one and the current term, and then if we do this nice syntax where it's case, we've got this with previous one and the current one. What we want to do is generate the sort of next pair of previous and current things. So the next previous thing is just going to be our current thing, kind of shifts over, and then the next current thing is going to be, as it says in the definition of what the Fibonacci sequence is, plus cur. And we also got to remember that this is going to give us an iterator of tuples, and we kind of only want single numbers rather than this double bracket thing here. So why don't we go ahead and just take out the just the second one. Oops. Call that x, and we'll just map it to x. I think you can use underscore dot underscore 2 or something in Scala, but let's see. And what I'm going to do is I'm going to just to see if we're right, just to see if this let's just take the first 10 or so, and print them all out and just see if this works for us, because I might have got this wrong, to be honest. Alright, so I'll do my usual sort of pause recording, do the compilation thing. If I can find my recording pause error, there it. Alrighty, so it looks like it's printed out 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, which you'll find is the same as that. So that kind of suggests to me that we're doing pretty well. So remember, we want to only keep the ones that are actually multiples of 2. So as we did before, that will be the thing percentage 2 for getting the remainder equals 0. If that's true, then it's a multiple of 2. And the final kind of bit for this problem, I guess, was we want to only keep the things that are under 4 million, so we'll just do this rather useful function, take while under 4 million, like that. And the final thing is to sum them. So let's go ahead and see what happens with this. Alright, well, it looks like it's done the work. It only took 0.83663 seconds, which honestly is kind of longer than I thought it would be. But again, like, we're probably just running a bunch of processes on my machine. So obviously right here we're going to check if that's correct, and it looks like it is. Great. I think we're about done, to be honest. Maybe I should explain what more of these functions do in more detail, but I mean, I'll only do that if people actually watch these videos, which, let's see. If you did stay to the end, thanks for watching again, and this is my second video, so hopefully it's slightly better than my first one.